Okay, chemistry time. I should have said all right. I'm trying not to say okay. That's my new thing. I don't want to say that word anymore. I want to say all right, chemistry time. Today we are talking about I think today and next time we're talking about bonding. So let's name it that. Bonding. We're going to talk about one type of bonding today. We will talk about another type of bonding with the next chapter in the future, but we're going to talk about bonding in general first. I think you know the first question I'm going to ask. So you ask it.
What is bonding?
The question is, what is bonding? What's the answer? Yeah, great. I'm just going to put exactly that. I think that's as good an answer as anything I've ever heard. Two things. I don't love the vague language of things, but actually in this case it really helps. Two things coming together. We might even, if I had to add anything, I'd say two things coming together as one. And that kind of reminds us of something like the language of a marriage vow, right? Two human beings coming together as one flesh. That's marriage. That's one of the ways that many of us think about marriage. There, depending on your culture and outlook, you might have different ideas about marriage specifically, but generally, and I think it's true anthropologically that for all of human, at least history, maybe not prehistory, but at least for human history, the norm of marriage has been two human beings coming together as one. So marriage is a kind of bonding. Marriage is a kind of bonding. Two things coming together as one also happens physically. Another addition I might make to this, we could put or more, right? It doesn't have to. Now, in the case of marriage, most of us, the normal idea of marriage is that it is specifically and exactly two. But in bonding, as we're going to talk about, in chemical bonding, that kind of goes without saying because this is chemistry class, but in chemical bonding, two or more things can come together and then behave as one entity. If we went downstairs from this room and asked Mr. Jones what is bonding, he might tell us this, but in shop class, bonding is taking two pieces of wood and gluing them together, right? And now they will behave as it were one piece of wood. So that's what bonding means, is for two things to come together. That's a bond. The marriage bond, or a bonding agent like glue, or again, chemical bonding. So let me ask you another question. What, as we learned in the last video or the last chapter, what subatomic particle mediates this bonding? What is the subatomic particle active in the bonding? Yeah, electrons. So this has to do mostly with electrons, and specifically valence electrons. And the number of valence electrons, its straight quantity of valence electrons, is what determines how an element or the atoms of an element will bond. So valence electrons are those that are involved in bonding. We usually say that electrons are the subatomic particle that mediates chemistry. That's the primary subatomic particle we're concerned with in normal or analytical chemistry. That is chemistry that isn't nuclear chemistry or maybe even organic chemistry, but chemistry to do with the majority of the elements. We're concerned primarily with the way their electrons behave. The type of bonding that we're talking about today is ionic. Bonding related to ions. We've already talked a little bit about ions, but what an ion is an atom that has a different number of protons from electrons. So remember, what we normally define as an atom is electrically neutral. That is, it has no electrical charge because it has the same number of protons and electrons. If you remember when we were talking about how to determine how many protons, neutrons, and electrons are in an element or a particular isotope of an element, we said that electrically neutral atoms have the same number of protons and electrons, but in an ion they don't. So this will be a charged particle because it's not just atoms that can become ions, but also groups of atoms. What do you guess, this is a little bit of a side note, but what do you guess we call a group of atoms that together has a charge? No? Guess again. A group of atoms, more than one atom, that has a charge. An ion that is more than one atom. You say it.
What?
An ion that has more than one atom.
Proton.
Nope, a mini atomic ion.
You said it wrong.
What's another word for many in Greek? A mini atomic ion. A polyatomic ion. If you remember, I said when I gave you your worksheet, I said that this is the chapter where our memorization of these polyatomic ions, these groups of atoms together having a charge, this is the chapter where those come in handy. Give me two examples, right? You were supposed to have 20 memorized, but give me two examples of polyatomic ions.
Cn minus 1.
Okay, what's Cn minus 1?
Cyanide.
Cyanide. Give me another example.
C2O4, -2.
C2O4. I really messed that up. -2 or 2 minus. At this point, it doesn't matter. Oxalate. I should have made you tell me. But these are examples. So if we were to diagram Cn minus 1, we would diagram, I'm going to use blue for nitrogen and black for carbon. And they together have a -1 charge. So these two things are bonded together, by the way, covalently. This should be review. This will also be preview because in the next chapter we're going to talk more about covalent bonding. But these two things are bonded together covalently, and together they have a -1 charge. They form a polyatomic ion. So an ion is any charged particle, an atom or a group of atoms that has a charge. Back to our valence electrons. Why are valence electrons related to ions? How does that tell us? For instance, if we look at oxygen on the periodic table, how many valence electrons does it have? 6. It's easy to tell from the periodic table because it's in group 16, or what we used to call 6A. So it has 6 valence electrons. How does that tell us how it will become an ion? How many does it?
How many are in each level, energy level, to tell you how many can change energy level?
Yep, it can. So it has 6 valence electrons in its outermost energy level, which is what valence means. And the octet rule, remember from last time, the octet rule tells us that it is, I sometimes say wants to, but it is most stable with how many?
8.
Yeah, with 8. And I'm going to put a little squiggly because it's not quite true. It's most stable with a full valence shell, which for almost all of the elements, for 116 of the 118 elements, that's 8. But for hydrogen and helium, which are hydrogen at least is pretty common, that's 2. So they're most stable with a full valence shell or orbital. We sometimes still use the word shell, even though orbital is more agreed upon. So, but we call it the octet rule either way because for most of them it's 8. So it's most stable with 8. It has 6. What's going to have to happen to it? Let me diagram oxygen here. Oxygen has 6 valence electrons. So here's the electron dot diagram. What's going to have to happen for it to become most stable? Gain 2. So now it has 2 more electrons. But, 2 things. 1, how many protons does it have still? Still has 6 protons. Otherwise, it wouldn't be oxygen. So that's got 6 protons. How many electrons does it have now? 8 electrons. So now it has a charge. It has a charge. Now it's not O anymore. It's O2 minus or O minus 2. It has become an anion, a negative ion. If it gains electrons, it's an anion, a negative ion. Second thing, so the first thing is it now has a charge. Second thing, I've drawn these arrows. Where did they come from? Exactly right. Good job noticing that. It has to come from another atom. Give me an example of an atom that could have given it 2 valence electrons. Nope. Sulfur has 6. It could have been sulfur. That's not impossible, but I'm looking for one that's a direct match. Nope, that one has 8. It got 2 valence electrons from somewhere. Who wants to give up 2 valence electrons? I shouldn't say which, Who would be most stable if it lost 2 valence electrons? Which one would be like a noble gas if it lost 2 valence electrons? No. Which group, if they lose 2 valence electrons, will all be just like a noble gas if they lose 2? Nope, that would be most like a noble gas if it lost 1. So which group? Group 2. So give me an example. What could have given 2 valence electrons to oxygen? Magnesium. Yeah. So these electrons went from magnesium. I'm going to draw those in blue also to show that they were eliminated. So magnesium had 2 valence electrons, and now it has not 0, right? It has magnesium would have 0 in its third shell, but now it has a full second shell. So it's stable according to the octet rule. And oxygen now has 8, also in its second shell, and so it's stable. But now we have magnesium. What? It's no longer just magnesium. Now it's magnesium. Well, it's how many protons does magnesium still have? No. 12. It still has 12. It started out with 12 electrons, but now it only has 10, right? 10 electrons. So now it's no longer just magnesium. It's magnesium. No. It has lost electrons. I know it's a little confusing. Yeah, 2 plus. It has formed a cation, a positive ion. So they're both happy, right? Magnesium is more stable. I shouldn't say happy. Magnesium is more stable. Oxygen's more stable. They both go on their merry way, right?
Yep.
No. Back to our marriage. Maybe the new way, Tatum, I don't know how high school is now, but maybe the new way is they both get what they need and they go on their merry way. But they should be bonded together. Why? Why do they bond together now? What bonds them together? What's hold? Not quite. I'm sorry, I didn't mean to scroll the wrong thing there. It has more to do with this. So the oxygen has a negative charge. This whole thing here has a negative charge, and the magnesium now has a positive charge. What's true of those? A positive charged magnesium, or anything, and a negative charged oxygen, or anything. They can't just leave, because what's holding them together? What's true of positive and negative charges always? Opposites attract. They're held together by the electromagnetic force, because opposite charged things always attract. And so it's true that magnesium has given its 2 valence electrons to oxygen, and they're both more stable, but they're now also bound together. Like marriage. They gave each other what they wanted, and now they're stuck, effectively. I mean, that's kind of a bleak way to look at marriage, but they're bonded together because they're opposite in charge. So 2 things that people sometimes have misconceptions about. It can't just get electrons out of thin air, right? I mean, look, thin air is made of matter. So what I mean is, that's a colloquialism, but I mean, it can't just manifest electrons out of nothing. They have to come from somewhere. And then when the electrons are transferred, there's a force of attraction between them, and that's called an ionic bond. That force of attraction is an ionic bond. And so they match in charge. In this case, they match directly, but what if instead of that, first of all, let's add a polyatomic ion in here. What if instead of that we had a polyatomic ion, like cyanide, for instance? So we have this cyanide here with a -1 charge. So even though the cyanide is bound itself covalently, it has a charge. What if the magnesium now, with a 2+ charge, right, bonds with the cyanide? Well, how many cyanides is it going to take to make the magnesium stable? The cyanide has a -1 charge, so how many cyanides is it going to take? Nope. There's a 2+ charge here and a 1- charge here, so we're going to have to do what? Yeah, we're going to have another cyanide. This other cyanide also has a -1 charge. And so now our compound is not just MgCN, it's MgCN2. And that's when we write the formula for compounds that have a polyatomic ion in them, we use parentheses to kind of, in a way, like keep the polyatomic ion together. Another way to think about it is this 2 distributes across the polyatomic ion, kind of like in math. So there's 2 cyanides, not 2 N's and 2 C's. There's 2 cyanides. So this compound, and now the last step of what we do with this is we name them. What's this compound called? We had MgO. Well, to name it, we just write the name of the cation, magnesium, and then we change the ending of the anion to ide, so it's oxide. This one, magnesium. If it's a polyatomic ion, we just use its name, cyanide. Most of what you will be actually doing on the test, like your activity for the test, where the math would normally be, is naming and writing formulas for ionic compounds. And to that end, a kind of tricky thing that's thrown in there is that when we have transition metals, first of all, let's talk about metals in general. Metals, we know, are on the left side of the periodic table, right? So these are all metals. One of the things that defines a metal, I'm just going to erase transition. We're just going to talk about metals in general first. Metals. One of the things that defines a metal is that when it bonds, it forms cations. That is, it would rather lose electrons than gain electrons. Do you see that? Why that would make it a cation? I should say it just forms cation. A cation has more protons than electrons, and so if they have a tendency to lose electrons, they will form cation. They want to lose electrons generally. Metals want to lose electrons. You know the other physical characteristics of metals: shiny, malleable, ductile, right? That was part of what you did in the last chapter. But metals form cations. That's the chemical definition of a metal. They also can bond. Well, so they would bond ionically with nonmetals or polyatomic ions. But they also bond, we say metallically. There's a metallic bond with other metals. So in a metallic bond, the nuclei, which I'm going to indicate with dots in this diagram, of metals, they don't even have to be the same kind of metals. Maybe there are some iron, which I've indicated with those black circles, and maybe there's some copper, which I'm indicating with pink circles here. And don't come at me with iron and copper don't really alloy like that. Maybe they do, maybe they don't. That's not really the point. But nuclei of metals, right? These are metallic nuclei, just the nuclei, are surrounded by a sea of electrons. We use the phrase sea of electrons, like SEA, like the ocean. Sea of electrons. They all, kind of like a hippie commune, they all share electrons amongst each other. All the electrons are kind of shared among the nuclei. They are free to flow. And the flow of electrons is electricity, which is the reason that wires, right, I just won't pick up on camera, but I'm touching a wire here, are made of metal, because electricity flows easily. Electrons that are here can easily flow through the metal. They're electrically conductive. That's also why they conduct heat. It's also why they're malleable and ductile, because if we have a hammer and hit this, and this one gets moved down a spot, well, it's still within the sea of electrons. It's still in this matrix, and it just has a dent in it now. Whereas, if we have an ionically bonded compound, let's say it's iron again, usually for one thing it'll form this repeating pattern. I'm gonna bracket this one so that my diagrams don't get mixed up. This one's ionic. So it has to be, again, it'll bond ionically. Metals will bond ionically with nonmetals. So we'll say it's iron oxide, FeO. So every iron is bonded to an oxygen like this. Again, don't come at me with that's not really the crystal lattice of iron oxide. I'm just trying to use this as an example. So we have, in this case, the red is representing oxygen. And there's an ionic bond between the iron and the oxygen. Right? They form this pattern called, again, and this is one of your vocab words, a crystal lattice. Oops, I'm supposed to be drawing. I'm kind of messing up, but this forms a crystal lattice. You know what lattice means? It's like, sometimes there's like lattice on top of pie. Have you ever seen a pie made with like the crust in strips on top of it? That's a lattice. Or like sometimes on the bottom of people's deck, they'll have kind of like wood X's. That's a lattice. Or like a chain link fence is a lattice. So this repeating pattern, this mesh, is called a crystal lattice. But if we hit that with a hammer, well, this whole row will move down one, and now we'll have, instead of iron touching oxygen, I said oxygen, right? Now we have oxygen touching oxygen and iron touching iron, and those will repel, right? Just like opposites attract, the same ones repel. And so instead of forming a dent like a metal does, an ionic compound will just split, and sometimes even explosively split. Does that kind of make sense why? So the ionic compound is a crystal, and one of the hallmarks of crystals is that they're not malleable, they're brittle. So that's true in an ionic compound.
The bond is with what?
With other metals. So metals and metals bond metallically. Good question. Metals and nonmetals bond ionically. Metallic is metals and metals. And ionic is metals and nonmetals, or polyatomic ions. And then the trouble with the transition metals, though, this is what I was going to talk about initially. The trouble with the transition metals, and it's not really a trouble, it's just like it's a fact of nature, but the transition metals can bond with more than just their valence electrons. They can bond with their d level electrons too. So you remember, for instance, vanadium would have an electron configuration of argon, 4s2, 3d3, right? So it has two valence electrons, 4s2, but it also can bond with its 3d electrons, its 3 third level electrons. And so vanadium can have multiple, you can even see here, can have multiple charges. So unlike magnesium, which is always +2, vanadium can be +5, +4, +3, or +2. So how do we determine whether it's vanadium with a 2 charge or vanadium with a 5 charge? Because that's really important. Those are different compounds. And the answer is that when we write it, we would write vanadium, for instance, 5 oxide. This is the charge of the vanadium. We write it in Roman numerals. You see V is, yeah, maybe that'll help. We always write it in Roman numerals. And it's especially confusing that I chose vanadium in 5 because V is 5 in Roman numerals. Beside the point. So the charge of the vanadium is written after. And so we would write that as, so what's the 5 represent? It's charge. And so it must be VO. But how do we know what the ratio is? Well, oxygen's always 2 minus. Do this in a different color. Oxygen's always 2 minus. If this vanadium is 5 plus, well, we must have 2 vanadiums and 5 oxygens. That's the compound V2O5, vanadium 5 oxide. And so there's a kind of a special case with transition metals when we go to name them. And the way to get good at these, and the way to get good at these, and these is just to practice. So that's what your worksheet is for. We're just going to practice writing names and formulas for ionic compounds. Do you have questions? Again, this is kind of a lot at once, but it should kind of be a review. We did do even these in physical science. I mean, I think all this stuff was brought out in physical science, but if you have any questions, let me know. And the main thing to do, again, is to write the names and formulas of these, is what we'll primarily be doing. Bye.